Do you guys know how the ring counters work? How the Johnson counters work? So let us discuss how the counter concepts and how the counters can be built with the help of registers here. So let us simply draw this instead of drawing the big diagrams. I have drawn with the register things. So each one is a flip flop, and I have indicated a common clock for all things. So all are synchronous clock. So I have decided I have wrote like this. So then the last output of the flip flop, which is connected to the first in flip flops input, so means this will be a counter, so the last thing will go inside. So let us draw a table and understand how this will be helped in counting, and how the process will take, how many used state will be there, everything let us discuss now. So this is the clock. So this is q3, q2, q1, q0. Okay, everything is sequentially connected. So at clock 0, this will be the initial condition. So let's take a condition which is 0 0 0. At clock 1, so as the last input only comes in, right? So if the all is 0, so nothing will happen. So here what we have to do is that we have to toggle the condition. So we have to apply some trigger. So I have given a trigger of 1 here. So rest everything will be 0 at the clock 1. Okay. So at clock 2, this 1 will be shifted to here. So this will be 0. So this last one will come first. 1 0 0. Third clock 0, this last one 0, this 0, the 1 will come here, the 0 will go here. The last 0 will come next first. So under the fourth clock, it will be 0 0 0 1. So here see, after the next clock pulse, what will happen? The 1 will come to this one. So this is nothing but our initial condition. So number of distinct state is there, only 4 distinct state. So because we are here, we are using only 4-bit registers. So number of used state. So number of used state which will be equal to number of used state which will be equal to 4. Okay, so that is nothing but n. So number of unused state will be 2 power n minus n. So this is unused state, right? So this is unused state. So the output frequency, how the output frequency will be getting divided is that we know whenever there is a toggling, the anything is happening, the circuit will also behave as a frequency divisor. So the T clock which will be divided by the number of state, that is n. Okay, so this is one very important thing, guys. So sometimes may they ask these kind of questions also. So the output frequency at a D naught. So D naught frequency which will be f clock divided by 4. Okay. So that much time only the changes will happen. So for the 4 clock of change in input, then only there will be only one change in the D naught. So that is what we usually call as a representation to this one. So few more thing is there. So duty cycle. So how we can calculate the duty cycle of this is the similar to the output frequency, that is 100% divided by n. So that much change will be happen. Okay. So I hope you guys able to get this point, right? So this is what how the clock pulses will be working. So here we have directly given the input like this way. So sometimes some in between gates will come, all the changes may happen, anything will be possible. So let us discuss more thing on this. So let we see one of the important question here. Sorry for the screenshots which was very blurred. Let me read it for you guys. Assume that all the digital gates in the circuit shown in the figure are ideal. A resistor which is equal to 10k and supply voltage is 5 ohm, and the D flip flops D3, D1, D2, D3 and D4. So D5 are initialized. So everything is initialized with the logic of, we have already mentioned 0, 1, 0, 1, 0. So these are the initial condition. So here the Q3 and Q5 are added and given to the resistance which is 10k. Okay. So they asking us to find out average power dissipated in the resistor R. So here you see the digital electronics concepts came into picture, and the network console came into picture, and everything. So these kind of questions will be called as miscellaneous question. So you guys may know how I will know I am studying digital electronics, so this network concept I may not know, so I have to skip this question. Then that is not a fine. So let us try how we can solve this. So let me draw a table so that you guys can clearly able to understand the things. So table is nothing but the output state changes. So this is clock. So this is Q1, Q2, Q3. From the day order I am writing Q3, Q4, Q5. Okay. So this is Q3 plus Q5. Okay. So they are addition, right? So at clock 0, what is the state that they given? So 0, 1, 0, 1, 0. Okay. At clock 1, what will happen? The last how the changes will happen? This is shift resistance. So which is 0, then last state, you see last state is connected to D1. So this 0 will come here. So 0 1 0, so 0 1 0 and 1. Okay, so after the clock 2, what will happen? The last input 1 will come here. 1 0 0 1 0. Okay, so third clock pulse, what will happen? 0 1 0 0 1. After the fourth clock pulse, 1 0 1 0 0. Fifth clock pulse, which is 0 1 0 1 0. Okay, so let us draw this one. So if we add here, that will be initial condition, so we are ignoring it. So q3 plus q5, which is 1 here. So q3 plus q5 is 0 here, q3 plus q5 is 1 here, and then this is also 1 here, and this is 0. So this is the 5 clock. We have 5 bit, so we have taken for 5 different states. So if we again loop it, then that will be initial condition only. So we have taken the 5 different states, right? So that's only we have took this one. So here we know the 5 clock pulse is completed. So t0, which is equal to 5 clock. Okay, so t0, which is equal to 5 clock, because 5 input is there. So here if you see how many times the output will be on means here the resistor I am calculating. So resistor side, how many time it will be on is the 3 times. So t on, which will be equal to 3 clock pulse, and t off, which will be equal to 2 clock pulse. Okay, so we have found out how many times the cycle will be on and how many times the cycle will be off. So, okay, so we have find out something here. So now we know the formula to calculate the power average, which is equal to, so I think this is prerequisite, some network background we need to have. So once we have completed network thing, we may have. So for now I am giving you the formula. So V square RMS divided by R. So this is what the formula, because we are given R here, so we have used here, and we have some related to voltage, because they are given supply voltage in the terms 5 volt. So that's why I am using this one. So how VRMS can be found out is the, so VRMS general formula, which is equal to square root of 1 by overall t 0 to t x square t dt. So this is what the formula to find out this. So here we are know that clock pulse is on for 3 and off for 2. So using this, let us represent this one. So V square RMS. So we are removing the square root here. So V square, the square root will be removed, right? So V square RMS. So the clock is 1 by 5t. So t clock I am representing as 5t. And if we take the integration, so we can clearly know at off time the output will be 0 and on time the output will be 1. So 1 is considered as 5 volt here. So let me write the thing. So x square means the 1 square, which is 5 square. So which is 5 square dt. How many times this is on? So 0 to t, 3t, because 3 cycle it was on, plus how many times it was off? That is 4t to 5t. So we can change this one, because we are going to find area only, right? So because integration is nothing but area. So I am arranging this together. So I am taking the 3 ones at one time and 3 off at another one time. So like this way. So here 3 and another one 2. So here 1 1 1 and here 0 0. So this is way I am taking. So this is the 1 clock pulse. Then this will repeat again. So I am taking this to 0 to t, and here this up to t, and this is 4t to 5t. Okay, so this is where I am taking. So if we take this, this is 0. So there is no impact on this. So that will be going to null. Okay, so if we solve this one, so what the answer will come is that, so 1 by 5t into, actually this is a constant, so this is 5 not a 3, so 25 into 3t, so 25 into 3t if we substitute integration, so tt will cancel, 5 will be 15, actually 5 into 3, this is 15. Okay, so this is what the answer. So if we substitute the same in the formula, so p average, if we substitute, then how the thing will come is that, so p average, which will be equal to, p average will be 15 divided by 10k. Okay, so we can clearly state that is 1.5 milliwatt. So answer is 1.5 milliwatt. Okay, so answer is 1.5 milliwatt. Okay, so guys understood the single then. So this is completely digital electronics. So just a counter. So from where we are converted the output into graphical waveform. So this is the graphical waveform. So now this is a networking or simple mathematics, anything. So here we have to use this into substitute here. So we have to take the integration accordingly, and then we have to apply the things. So after that, so 15 divided by 10k, that is 1.5 milliwatt. So that is what the answer, guys. So I hope you guys able to understand. So these are some kind of 2 mark questions that are asked in GATE examination. So this will be very helpful if you guys solve these kind of miscellaneous concept, and the concept of networking and digital electronics, and the concept of EDC along with the digital electronics. So these will be very much helpful. So we'll be solving this going forward. More kind of questions will be solving like this. So next question, the shift register shown in the figure is initially loaded with a bit pattern that is 100. So here there is a 4 clock shift register, right? So let me again draw a counter table here. In digital drawings, everything is stable, K-map like this only. So we guys can easily solve any kind of question. So here clock. So firstly it was loaded with 1010 as they given, right? So 1010. Subsequently, the shift register is clocked. So whenever we are giving the clock, so first clock will come, right? So with each clock pulse, the patterns get shifted one bit to the right side. So this is right side shifting. So with each shift, the bit of the serial input is pushed to the MSP. So last bit of the thing will be pushed to MSP as shown in the diagram. So after how many clock pulses, we will be able to get again 1010. So how many number of used state will be there? So that is what the question. So thing is that, so if we take this as a Q3, Q2, Q1, Q0. So here you see the Q1 XOR with Q0. And this output is again XOR with Q2. So this is a bracket, okay? So let us solve. So if we XOR these things, so let us for the first clock pulse, if we XOR the 0, which is XORed with 1, which is XORed with 0. So this output will be 1. So then if the 0 is XORed with 1, then output is 1. So the MSB will be changed to 1. Then this is shifting to this side. So 0 will shift here. So 1 will shift here. So again, this 2 XOR is 1. When this is XORed with 1, then the input will be 0. Okay. So after second class pulse, it will be 1, 1, 0. Okay. So similarly, please pause the video and try to complete the rest of things. So this will be very easy question only. So after third clock pulse, 0, 0, 1, 1. Fourth one, it will be 0, 0, 1. Fifth clock pulse, 1 XOR 0 is 1 and this is XOR with 0, that will be 1. So 0, 0, 0. So 0, 0, all everything is 0. So XOR will also be 0. So 1, 0, 0. So 0 with XOR with 1, this is 1. So 1, 0, 1, 0. So here you see the initial condition which was attained here. So after how many clock pulse we were able to attain the thing is that, so this is preloaded condition. So sorry, I am mistakenly wrong to the another one. So this is not our condition. So here is the thing. So this is the initial condition which is at 0th clock. So after 7 clock pulse we were able to achieve the output. So the answer is 7. So 7 clock pulses we needed. So 7 clock pulses. So this is the correct answer. So I hope you guys are able to understand the things, right? So here every question which need to be solved like this way only. So like this way only, all the counter question can be easily solved with the help of these kind of simple tables. So I am leaving this here, guys. So from next classes, let's start more discussion on the other counters. Like many counters we have, it's like a pattern counter. So we have seeing the clock, right? So clock, how the stop time are going, right? So 0, 1, 2, 3. So let us discuss how that discussion is, how that circuit is designed and how the Johnson counter is designed. So and then we will be discussing some random input, like decide how we are converted from one flip flop to another flip flop. Similarly, some expected counters we need 0, 1, 2, 3 or 1, 2, 3, 5. So any random counters also we will be discussing how to analyze the circuit and also how to create the circuit. So we will be discussing that detailing from next classes. So please stay tuned, guys. Please like, share and subscribe the channel for more videos like this.